In the previous video, I introduced linear regression and how the whole idea of machine learning revolves around minimizing the loss. Supposedly, this linear line is a line that minimizes the error, and there are mathematical ways to accurately place this line in the graph. But this is a machine learning video, and from now on we're going to approach things in the machine learning way. To find where exactly to put this line is to try a bunch of ways until the line seems to be where the error is minimized. And if this machine learning way seems like a total garbage way, the next video will help you, I promise. Anyways, loss that is minimized doesn't really mean that it's zero. In fact, you can quite clearly see that the line doesn't exactly match the points in the scatter plot, meaning that this line isn't a 100% accurate prediction. That's pretty obvious because, well, the line is linear. You can't possibly draw a straight line that touches the points directly. But if we're able to bend and manipulate the lines like this, we can end up with a loss that is less than when the line is linear. And it doesn't seem impossible to make the loss zero if we wanted to, doesn't it? Yet, linear regression remains the de facto standard across pretty much everywhere that uses statistical analyses. Can we not train a machine learning algorithm to learn like this instead? We certainly can, so why don't we? Well, if you're asking someone why linear regression is used, you'll get a response like it's reliable, effective, simple, and easily interpretable. These are all good and valid reasons why linear regression is helpful for us humans, but you might be thinking, if a machine is learning, we don't need it to be simple or interpretable. The whole point is that machines can do complicated things, isn't it? Let's suppose there's some data, and when you plot out a scatterplot, it looks something like this. For explainability, there's 150 data points here, and they roughly follow a sine-shape relationship. But we've also added in some noise so it looks like a relationship you can find in some real-life trend. In data science, there's an important practice called splitting your data. You put them into train and test datasets. The idea here is that there's a subset of the data that you use to train a machine learning model. The model would only learn from the data that is in the training set. And you use the test dataset, which the model has never seen before, to evaluate how effective the model was. Let's apply that here as well. We split the original 150 data points into 120 data points to train and the remaining 30 to test. Important to notice that although we split the data, we can see the same general sine graph shaped in both subsets. Both the training and test datasets should represent the same real-life trend. So let's take a closer look at the training data only. You fit an ML model to the data with 3 different regression lines. The line on the left graph is a line that is fitted using linear regression or degree 1. The graph to its right is fitted using a polynomial regression of degree 4. And the rightmost graph has a regression line of degree 15. So tell me, which one looks the most predictive to you? If you thought that the line with degree 15 was the best one, congratulations. You just fell into the trap of overfitting. And I'm writing this in big red text because this is, well, really bad. Overfitting is another way of saying that the training is too good for it to be performant on the test dataset. It's trained too aggressively with the training dataset that it isn't generalizable to other datasets. In other words, it struggles when it sees new data. Think of it as a student who studied using a practice exam too much, that the student just ended up memorizing the practice exam instead of understanding the concepts. And when the student received the actual exam that is obviously a bit different from the practice exam, the student didn't perform well on the actual test. Let's look at what happens when we use the degree 15 regression on the test dataset. Pay attention to the graph on the right. Here, the red line represents the evaluation or the predictions of the degree 15 regression evaluated on the test dataset. It learned the patterns of the squiggly black line and is trying to apply it to the test data. Well, because it used the training data too specifically, you can see some weird things going on in the red line, like the diverging lines at the end of the graphs and some gaps that make these predictions a little bit off from the training regression line. This basically represents a learned model that performs poorly when it sees new data. And as I claimed in my previous video, a machine learning model exists to help humans make decisions in the face of uncertainty. And a model that doesn't perform in uncertainty is not a good model. The concept of underfitting also exists. It's the opposite of overfitting, where the model used is too simple to represent the actual trend. But this is not really considered to be as bad as overfitting in the data science world. That's because a model that is simple still generalizes quite well. Can you spot the black regression line in this left graph? No, but that's because it's almost exactly the same as the red line, so it's hidden behind the red line. And that means even though the predictions may be too simplified, the model can still do a decent job at predicting new information without too much error. This is why many people stick with linear regression, even if it's considered too simple. But ideally, you want to find the sweet spot of capturing the complexity of the data and being generalizable. And this middle graph does this quite well. The degree 4 model appears to be a good blend of both. The bottom line here is that we want to find the right balance between complexity and generalization. How do we do this? Well, the fun thing about machine learning is that it's as much art as it is science. There's many things in machine learning where the decision that you have to make as a data scientist just has to come from experience and intuition. But to give you a bit of guidance, many data scientists abide by what's called the Occam's razor, or the principle that the simplest usually is the best. And data with more convoluted patterns than this one, it turns out, are pretty rare in real life. That's why a lot of data analysis just starts with linear regression, often as a baseline model. Still, linear regression isn't always the answer. We capture other patterns with non-linear regressions like logistic regression or regularization techniques like ridge regression and lasso regression. And we also have other ways of addressing complexity through feature engineering, such as adding polynomials, which is what we saw with our example, adding in interaction terms, and transforming of variables to manipulate how linear or how non-linear we want data to be. When we get to neural networks, we'll also introduce activation functions and how they can be used to introduce non-linearity to linear models. But more on these later. Point is, there's a ton of ways to manipulate a linear model to make them be able to capture more complex trends. And so, linear models turn out to be a very good starting point, although you'll quickly need to get out of there. But a model that is overfit is a big no-no. Oh, and one last thing. A linear model makes gradient descent easier, which our next video will be about.